Hi there and welcome to lecture 11 of KV4000, in which we're going to be talking about graphics, specifically image files. So all of the graphics that we've used so far have been algorithmically generated. So we used the basic drawing primitives available to us as part of the processing toolkit, like circle, ellipse, rectangle and so on, to directly draw things like the bouncing ball and the bricks in Breakout and the route on the map and so on. And this is all great, but sometimes we want to be able to handle images that have been created outside the processing framework, that is JPEGs and so on. And obviously lots of apps make use of image files, so it's useful to see how processing handles these. Apart from giving you some additional programming tools, I hope it will give you some insight into how features that we rather take for granted in apps can quite easily be implemented. But before we start, we just need to familiarise ourselves with a couple of core concepts, the first of which is translation. So hopefully by now we're used to the fact that the origin in processing is located at the top left, but we can move this around if necessary. And this is generally used when we want to move objects around but easily maintain the same coordinates for them. So we can effectively plot the same object with the same coordinates, dimensions and so on in multiple locations by shifting or translating the effective origin to a new position. And this is obviously useful as it allows us to effectively duplicate objects as well as being able to move them around. So we can displace or move the origin using the translate method, and this takes in two arguments, an X shift and a Y shift, which are then added to the current origin coordinates. And notice that they're relative rather than absolute. So if the current origin is, for example, 1020, then translate 2030 will shift the origin to 3050. So here's an example. So we begin by drawing a square at 0, 0, with width and height 55, it's purely arbitrary. We then translate the origin by 50, 20 and then repeat the draw using exactly the same call as before. But you'll notice that because we've translated the origin, it's now drawn at 50, 20 here. Now if we translate by 2020 and repeat the draw a third time, then we now display the square at 70, 40. So you can see how the same call 3 times results in 3 different squares because of the 2 translations. So here's another example, this time showing how we can use translate to essentially replicate an item across space to form a sort of movable site or frame. So you can see the frame moving according to the mouse, and every time the mouse moves it takes with it this sort of movable frame. So in draw we get the mouse coordinates and use the constrain method to force them to be within a certain range. That is, any values outside that range are just discarded and default to either the maximum or minimum. So there's the minimum, there's the maximum. So the constrain method basically just takes in a value, okay, and if it's within this range then it just returns the value back. Otherwise, if it's outside the range, in either direction, it just returns either the minimum or maximum, and this just keeps everything inside the frame. So we then perform a translation to the current mouse location and draw a blob, draw a circle. So this one here. We then translate the origin 100 pixels to the right, but keep the Y the same, and draw a blob again, so this one here. We then translate 100 pixels down, do the same draw again here, and then translate 100 pixels to the left. And you'll notice how the negative 100 means a translation to the left, and we draw this blob here. So you can see how the same ellipse, the same call to ellipse 4 times has resulted in circles being drawn in 4 different places because of the translation. And you can see how these translations are summative in the sense that every time you call translate, it adds these values to what the current location of the origin is. So now that we understand translation, let's consider how we use it to deal with image files. So just like any other files, these are just data files which we generally visualize as a sort of 2D matrix of pixels. Now we'll show how to get inside these files and deal with the data inside them shortly, but let's first talk about how we can just display them in our processing app and how to manipulate how they're displayed. Now of course processing comes with a bunch of tools for playing with image files, and the one that we'll use is the pimage or processing image class, which contains all of the functionality that we'll need for loading and displaying image files as well as manipulating them. So just a note on files and how they're managed. When we deal with images, processing by default stores them in a folder called data, which is inside the sketch folder. So if you handle any images within your sketch, they will be by default looked for by the sketch in a folder called data. Now you can either add images to the sketch directly by just dropping them in the file manager into that folder, or by using the processing sketch add file menu option. So here's a simple piece of code to load in and display an image. So it's a JPEG of a smiley face that we've downloaded from somewhere else, and here's what happens when we run it. Okay, so it's not quite what we wanted because the image file is deliberately large, 463 by 455 pixels, so much bigger than the canvas. So we'll worry about this later, but it serves to illustrate an important point. So let's look at the code. Well, first of all, we declare a pimage object called image here, and then in setup we load in the file using the load image method and a file name. Okay, and again, if you just specify the file name without any path or anything, it will look in the data folder first of all for it. So what this does is essentially takes the data in the file, extracts it from the file, and then inserts the image data into the image object. Okay, so that sort of embeds the image data inside a pimage object. In the draw method, we just clear the background as usual, and then we use the image method to draw this particular image at 0, 0 at the top left of the canvas. So let's resize our smiley to be rather more usefully proportioned. So we can call the resize method on any pimage object to change its dimensions, and this takes in two parameters, a width and a height. Now if we specify 0 for either, then the resizing is scaled proportionately, rather like locking the width and height together if you do a file resize in an app. But this essentially resizes image to be 50 pixels, and you can see how when we draw again, you can see how it's drawn in a much more sensible size. So the question is, what fun can we have with this little smiley face? Well, what does it remind you of? Well, we'll look at that in the next movie.